Hi there, Mr. Sutton here, bringing you these AB Calculus 614 Extra Practice Number 5 solutions on volumes with known cross-sections. For this problem, we have the base of a solid being the region in the first quadrant, bounded by the y-axis, the x-axis, and the graph of y equals e to the x, and the vertical line x equals 1. For this solid, we want each cross-section perpendicular to the x-axis to be a square, so what is the volume? So we're going to need to find the area of the cross-section, and then we're going to need to find out the limits of integration. So for the area, well, they said that the cross-section perpendicular to the x-axis was a square, so that's the shape we're going to be integrating over some interval. So I'm going to write a of x equals s squared, and I'm writing a of x because we're perpendicular to the x-axis. So this is going to be a function of x. It's going to change with the x value. Now the square here, this is a square that's basically coming out of the xy plane. So the base of the square, one side of the square, is just going to be the distance between the top and the bottom of the bounded region. So it's basically just going to be e to the x minus the x-axis, which is just going to be e to the x. So that's going to be e to the x squared, which I can turn into e to the 2x if I want to. And now I just need to integrate this area over the interval from, well, let's see, they said we were bounded by the y-axis and the line x equals 1. So that's going to be the integral from 0 to 1 then of e to the x dx. All right, let me go ahead and actually use my fundamental theorem to evaluate this. Antiderivative of e to the 2x, that's going to be 1/2 e to the 2x. You're just doing e to the 2x divided by that inner derivative of 2. So I can yank a 1/2 out of there. Although, actually, it's not too much trouble. Let's just keep it in there. So we have 1/2 e to the 2 times 1 minus 1/2 e to the 2 times 0. This is just 1/2 e squared minus, well, this is going to be 1/2 because you're doing 1/2 times e to the 0, which is just 1/2 times 1. And this ends up being answer choice B. For this no calculator problem, the base of a solid is the triangular region in the first quadrant, bounded by the graph of this line, the x and the y-axis. For the solid, each cross-section perpendicular to the x-axis is a square. What's the volume of the solid? So we have this triangular region, and each of the out of each of the kind of the vertical heights in this region, we have squares growing kind of three-dimensionally. So to find the volume of the shape that's formed from all this, we just need to find the area of a square in terms of x, and then just integrate that from left to right. So let me get my left and right limits of integration. We know that we're bounded by the y-axis, so we're starting at 0 for the x values. And how far to the right are we going? We're going as far as it takes this line here to intersect the x-axis. So let me start by setting this 5 minus 5/3 x equal to 0, so that we can find our upper limit of integration. So if I subtract 5, actually, it'd probably be easier if I just add this 5/3 x over there. Now if I multiply by 3/5, or actually, 3/5 on both sides, that's going to cancel out this 5/3. On the left side, that's going to give us, let's see, 3/5 of 5 is just 3. So that's our upper limit of integration. We're going to have an integral from 0 to 3 at some point. But now I need to figure out the area formula of these squares. So in general, a of x is going to be s squared. I'm going to need to write something in terms of x that matches this square area sort of format. Now the side of the square is just the distance between this line and the x-axis. It's just from one end of the bounded region to the other. So the distance is just going to be this formula right here. So for s, I just have 5 minus 5/3 x. So I'm going to be squaring that now. And I'm going to be integrating this over the interval from 0 to 3. So my volume then, integral from 0 to 3 of this stuff, dx. But because I'm going to have to do this by hand, I'm actually going to expand this. So let me see here. This is going to be a squared plus 2ab plus b squared, so 25. And then I have to multiply these and double it. So this is going to be, let's see here, negative 25 over 3 x, but I have to double that. So that's going to be 50 over 3x. And then I have to square this last thing, so that's going to be 25/9 x squared. All of that with a dx. And now I'm going to take the antiderivative of all this using my fundamental theorem to plug in 0 and 3 afterwards. So going left to right, we've got 25x minus, now this bumps up to 2 for the exponent. Dividing by that, I've got, let's see, 25 over 3 x squared, and we're subtracting that. And here, this bumps up to a 3. Dividing by that, I'm going to have a 27 down there, so 25/27 x cubed. All of that evaluated from 0 to 3. And the fun just keeps coming. We have to plug 3 into all of this stuff. And then we're going to have all that craziness with 0 plugged in, subtracting all that. There is a little bit of an array of good news here. When you plug 0 into all of those things, because they're all being multiplied by 0, this entire second bracket just gets wiped out. So really, we can just focus on this first bracket. We do have to simplify it because the answer choices are all simplified. So going from left to right, we have 75. And then here, this is going to be 9 divided by 3 is 3, times 25 is also 75. So we have 75 minus 75. Well, that could be a lot worse. So really, those two terms cancel out, and it's really just down to this term here. Now, we've got some more good news. 3 cubed is 27. So 27 divided by 27, that's canceling out, leaving us with 25 here. So when the dust settles, we just have 25 for the final answer, giving us choice C. On this problem, we're told that the base of a solid is the region in the first quadrant, bounded by y equals cosine of x and the two axes between 0 and pi over 2. And then for this solid, each cross-section perpendicular to the x-axis is an equilateral triangle. We want the volume of the solid. So let me graph this out so we can get a better picture of this. So I've entered cosine of x in my y1, and for my window, let me just go from 0 to pi over 2, because that's the window they specified. So pi over 2, and then zoom 0, zoom fit. All right, so here's the bounded region we're talking about. So apparently we have some equilateral triangles growing three-dimensionally out of this. Now the way the setup works, the base of the triangle is basically going from the top to the bottom of this bounded region. So this distance here is giving us the base of the triangle. Our goal at some point is to write an area formula for this triangle in terms of x, and then just integrate that area formula from left to right using an integral. So we have to get an area formula in terms of x. To get that, it would help if we just had an area formula in terms of the base of the triangle. So here's an equilateral triangle. We know that all three sides are the same. So this S down here, this is going to correspond to that distance from one end of the bounded region to the other. And that distance is just going to be cosine. So if we can express the height of the triangle also in terms of this S, then we can also express the height in terms of this cosine function. Well, this is a little bit tricky. In order to get the height in terms of S, let me drop an altitude here and do a little more analysis using some special right triangles. When I do this, I'm splitting this up basically into two 30, 60, 90 triangles. Now we know that the ratio on these, if you remember your special right triangle days, the side across from 30 we called S, across from 60 was S radical 3, and across from 90 was 2S. So that means that since we're splitting this in half essentially, that means this little side down here we can think of as this, that's this S side, but it's really like half of this S. So there's different S's going on. Probably should have used a different letter here, but I'm going to call this like other S over 2. And then this 60 side here, this is going to be whatever this little side was times the square root of 3. So this is going to be over here S radical 3 over 2. So the long and short of it is the area of this thing, which is in general base times 1/2 base times height, it's going to be 1/2 base of S times a height of S radical 3 over 2. So if I clean this up a little bit, I can write s squared radical 3 over 4. And now since this s down here is really just cosine, because again it's the distance from one end of the bounded region to the other, this is just going to be cosine squared of x radical 3 over 4. So there's my area formula that I'm going to be integrating from, let's see here, we said from 0 to pi over 2. So let me just go ahead and integrate a of x dx from that using the calculator. To try to make things a little cleaner on the calculator, I'm going to do some work in the y equals. I'm basically going to enter this a of x function in my y equals. So let me see here. Let me do alpha y equals to get my fancy fraction mode. And upstairs we're going to have cosine squared, which I can do just alpha trace y1 squared for that, because that was my y1 function. I'm multiplying that by radical 3 and dividing all that by 4. There we go. And now let me just quit out of there and do an integral. So math 9, integral from 0 to pi over 2. And we're doing just alpha trace y2 now, because that's where I stored my a function, dx, and all this comes out to 0.340. So that gives me answer choice A. For this problem, we have this region R bounded by x squared and 2x, and we're told that this region is the base of a solid where the cross-section perpendicular to the x-axis is a square. So we have these squares essentially growing out of this region three-dimensionally, and we want to find the volume of the whole thing. So in order to do this, we're essentially going to be taking the area of a square, some square slices, and integrating that from left to right. Let's start by getting our limits of integration, and then we'll talk about the area formula that we're going to have to use. So taking a look at this bounded region, it looks like we're starting at 0 and ending at 2. But let's just kind of analyze this a little bit more. So basically figuring out where x squared and 2x intersect. If I plug in 0 on both sides, I get 0 squared equals 2 times 0, so that works out. So 0 is the left limit of integration then, and it looks like 2 is the right limit. If I plug in 2 on both sides, 2 squared and 2 times 2 also is the same thing. So yeah, 0 to 2. Okay, so then let's get the area formula. For a square, we can write a of x equals s squared, but this does need to be a function of x in order for me to actually integrate it. So let me express this in terms of x now. So the side of the square, these squares are growing perpendicular to the x-axis. So the base of the square, you could think of it as, is going from one end of this bounded region to the other. This distance between the edges of the bounded region is basically just going to be your upper function minus your lower function, which in this case is going to be 2x, the line, minus that parabola x squared. So I can write 2x minus x squared quantity squared. S is just 2x minus x squared. And we're squaring that. Now I'm going to have to take the integral of this thing from 0 to 2. In order to do that, though, since I don't have a calculator on this, I'm going to have to expand this, take an antiderivative, do that whole dance. So let me expand this now. Using a squared plus 2ab plus b squared, this is going to be 4x squared, so 2x if I square that. And then I have to multiply these together and double it for that middle term. So that's going to be negative 2x cubed times 2, so negative 4x cubed. And then squaring this last term, we're going to end up with plus x to the 4th. And I'll have a dx in there. So going left to right, taking the antiderivative with the reverse power rule, this first exponent bumps up to a 3. Dividing by that, we have 4/3 x to the 3rd. And then this next one bumps up to a 4. Dividing by that, we have minus x to the 4th. And finally, this bumps up to a 5, giving us 1/5 x to the 5th, all evaluated from 0 to 2. Well, this is going to be a mess, but I have all of this stuff with 2 plugged in, minus all of this stuff with 0 plugged in. And here's a little bit of good news. All of this stuff with 0 plugged in is just going to be 0. So really, it's just this first bracket that we need to sort out a little bit. We are going to need to simplify this, unfortunately, because the answer choices are simplified. And again, this is no calculator, so hopefully you brought your fraction hat to help you with this. So going left to right here, we have 8 when you cube the 2 here. So this is 4 times 8 over 3, so 32 thirds. Next, we're subtracting 16. And over here, this is going to be 32 times a fifth, so 32 over 5. Let's clean this up a little bit. To add these together, I need a common denominator. It's looking like, given a 3 and a 5 here, 15 is going to be my common denominator. So I need to multiply this first fraction by 5 over 5. That gives me 160 over 15. This next one, 16, I have to multiply that by 15 over 15. Well, what's 15 times 16? I don't know. But I know that 4 times 15 is 60, and 16 is 4 times 4. So that would be 4 times 60, so 240 over 15 then. So we're subtracting 240 over 15. And then this last one, we need to multiply by 3 over 3, so 96 over 15. Still a mess, but we're getting there. So we've got 160 minus 240. That's going to be negative 80. Plus 96 is going to be 16. So we have 16 over 15. And that's as good as it's going to get. So that's going to be answer choice A. On this one, we have this region R bounded by the graph of 4e to the x plus 2, so an exponential graph. The line x equals 1 and the x and the y-axis. R is the base of a solid whose cross-sections are perpendicular to the x-axis are semicircles. What's the volume? All right, so we have this, this region in the first quadrant where you have this exponential function and the x-axis and also the line x equals 1, giving you kind of a triangular-shaped sort of area. And out of this triangular-ish kind of shape, you have these semicircles growing. We want to find the volume of that situation. So we're going to need an integral for this eventually. The limits of integration, we're essentially going from the y-axis to x equals 1, so that's going to be from 0 to 1. So that's already kind of taken care of. But now we're going to need to find the area formula that we're integrating over that interval. We're taking semicircle slices and adding them together. The area of a semicircle in general is going to be 1/2 pi r squared. But we need to write this in terms of x in order to get some kind of x function that we can actually plug into an integral. So we need to express the radius then in terms of x, because that's the only thing that really changes with these semicircles. Now these semicircles are going from one end of this bounded region to the other. All the way across, you basically have a distance of 4e to the x plus 2 from the x-axis. So this function here is the distance across with these semicircles. But this is giving you the diameter of the semicircle. If you want the radius of the semicircle, you actually need to take half of this distance across. So we can write 1/2 pi times, and now we're going to write 1/2 of all this stuff, quantity squared. So again, I'm taking half of 4e to the x plus 2, and that is giving me the radius that I have to rewrite this with. Okay, so I can simplify this a little bit here. I'm going to write this stuff out in front as just pi over 2, just looks a little bit nicer. And in here, this is going to be 2e to the x plus 1, and that whole thing now is being squared. So this is my area formula for these semicircles. I'm going to be integrating this from 0 to 1. So I've got volume equals 0 to 1. And I'm going to pull this pi over 2 outside the integral just to make my life a little bit easier. And while I'm at it, let me just expand this, because I'm going to have to do this by hand using the fundamental theorem. So this is going to be, let's see here, we have a squared plus 2ab plus b squared kind of set up. So squaring this first term, that's going to be 4e to the 2x. And then multiplying these and doubling it, that's going to be just 4e to the x. Plus, this last thing squared is just 1. And I'll put a dx in there just so it's mathematically proper. Taking my antiderivative from left to right, and I still have this pi over 2 outside here. This first one, we have 4e to the 2x divided by that inner derivative of 2. So this is actually 2e to the 2x. And then this next one is just going to be 4e to the x, so that's not so bad. And then this last one with the reverse line rule, this is going to be a plus x. And again, all this is evaluated from 0 to 1. So I have pi over 2 times all of this stuff with 1 plugged in minus all of this stuff with 0 plugged in. Now, if this were a free response, these are all constants, so you could leave it in this form and call it a day. Unfortunately, this is multiple choice, so you have to simplify a little bit here. Let's clean things up. In this first bracket, this is just going to be 2e squared plus 4e plus 1. And over here, let's see here, this is 2 times e to the 0, which is just 2 times 1, which is just 2. So we're subtracting 2. And this is going to be 4 times 1, which is just 4, but we're subtracting that as well. And then 0 obviously is 0. I'm cleaning things up a little more. One thing, at this point, you should look at the answer choices and see what kind of form these things are in. And you'll notice in all of the answer choices, we have a pi outside of parentheses rather than a pi over 2. So it looks like I'm going to have to divide everything inside here by 2, basically distribute the 1/2 that's there. So I'm going to have just a pi outside, and inside I've got 2e squared divided by 2, which is just e squared. 4e divided by 2 is going to be 2e. And finally, we have a 1 minus 2 is negative 1, minus 4 is negative 5, over 2 to get that negative 5/2. Looking at my answer choices now, this is going to match answer choice A. So that is our answer. For this no calculator free response problem, we've got this R region enclosed by the g of x and h of x functions. And we also have, let's see, the y-axis and the vertical line x equals 2, so that's 4 sides to this thing. First task is to find the area of R. So our general setup here, we're taking an integral from left to right, and the integrand is basically going to be top function minus bottom function to get this area. So on the left we have 0, on the right side we have the x value 2, so integral from 0 to 2 of top minus bottom. Well, we have to figure out which one is which. So it's looking here like this cosine function is going to be, I believe that's the bottom function, and then this parabola basically is going to be your top function. But if you're not sure, I mean, you can plug in 0 for x and see what we get. If I plug in 0 for x on this first function, that's just, let's see, cosine of 0, which is 1. 3 times 1 is 3. 3 plus negative 2 is going to be 1. So yeah, this ends up being the cosine function here. Just to really double check, if you plug 0 into this other function, this is going to be 0 minus 1 squared is just 1. So we're really doing 6 minus 2, which gives us this y-intercept here of 4. All right, so we're going to be doing then h of x minus g of x in here. So we're going to have to do this by hand because this is a no calculator question. So I'm going to expand this out now. I've got this h of x function, so 6 minus 2 parentheses x minus 1 squared, minus this g of x function. And now if I'm subtracting this whole g of x function, I'm basically distributing a negative to all the terms. So let me just do that right away. So this minus 2 is going to be a plus 2. This plus 3 cosine is going to be a minus 3 cosine. Still have the dx there. I've got my proper notation. At this point, I'm going to take the antiderivative. Now, I know that I can combine the 6 and the 2 together to get an 8. Antiderivative of 8 is going to be 8x using my reverse line rule. And now I have this next term. I could expand this term if I wanted to and then use the reverse power rule. However, I could also just, since I have an inner function that's just linear, I can just use my, my inner linear kind of mini substitution shortcut. So taking the antiderivative of negative 2 times something squared, that bumps up to an exponent of 3. So this would be negative 2/3 times something cubed divided by the inner derivative, which is just 1. So this would just end up being the negative 2/3 x minus 1 cubed. So not too bad there. A little bit nicer than having to distribute all of that and, you know, take our reverse line rule. Now we also have this cosine function to deal with. So this would be normally negative 3 sine of pi over 2x, but we have to divide by that inner derivative of pi over 2, which means we're really multiplying by 2 over pi. So this would be out in front 6 over pi sine of pi over 2x, and that would all be negative. So this is a fine mess. We're going to have to plug 2 into all of this stuff, like so. And then we're going to have to subtract all of this craziness with 0 plugged in. So you've got all constants at this point. That's the good news. You could actually just stop here and move on to the next part. But if we wanted to simplify, let me show you what that looks like. So we're going from left to right here. We're going to clean this up a bit. We've got 16. And for this next term here, well, 2 minus 1 is just 1. 1 cubed is 1. So this is just minus 2/3. For this next piece, let's see, these 2's cancel. You've got sine of pi, which is just going to end up being 0. Over here we have minus 0. For this next term, this is 0 minus 1, so negative 1. Cubed is negative 1 times negative 2/3 is positive 2/3. But wait, we're negating everything in here, so it's negative 2/3 again. Good times. And then over here, this is again sine. This is going to be sine of 0 this time, which is just 0. So that works out nicely. So we've got a whole bunch of zeros. We've got 16. We've got a minus 2/3 and a minus 2/3. So this is going to be 16 minus 4/3. Well, 16 is really 48/3. So we have 48/3 minus 4/3, which is going to come out to 44/3, if you really wanted to simplify that as much as possible. For this part of the problem, we're told that this region is the base of a solid, and for the solid, at each x, the cross-section perpendicular to the x-axis has the area a of x equals 1 over x plus 3. Find the volume. So we're just taking a bunch of area slices, each of which has this for the area, and integrating that from left to right. So this is actually not a horrible thing to have to do. We're going to use the same limits of integration as before. So volume now is going to be the integral from 0 to 2. And now we're just integrating this area formula from left to right. So this is going to be just 1 over x plus 3 dx in there. That's all we have to do on this one, is add up these area slices. So the antiderivative here, because I do need to do this without a calculator, this is going to be ln absolute value of x plus 3, evaluated from 0 to 2. So I have all of this with 0 plugged in, or 2 plugged in rather, minus all of this with 0 plugged in. There we go. And these are all constants, so you could just stop here, or you could write ln of 5 minus ln of 3. And if you really wanted to be fancy, you could combine these using log rules. If you're subtracting logs, you're dividing the stuff inside. So fully simplified, this would end up being ln of 5/3. For this last problem part, they want us to write but not evaluate an integral expression giving the volume of the solid generated when r is rotated around the horizontal line y equals 6. So let me just go and draw that line up here. So let's see here. We got 1, 2, 3, 4, 5, 6 right up here. So if I'm revolving this region around this line, just like before when I did the volume, I need some area slices that I'm adding together. Since I'm doing a volume of revolution here, solid of revolution, I know that I have to use either discs or washers for my area slices. And since I have some space, a gap between the bounded region and the axis of revolution, that tells me that I have to use washers for my area formula. So I've got a of x equals pi times big R squared minus little r squared. Big R squared is going to be the distance from the axis of revolution to the further away part of this bounded region. So that's going to be 6 minus this function down here, which, remember, this was our cosine function. This was the g function. So 6 minus g of x. Little r squared is the distance from the axis to the closer part of the bounded region. So that's going to be 6 minus h of x. And so now I'm just going to do the integral from 0 to 2 of, well, a of x dx. Now, I can actually just leave it like this if I wanted to, because I did define what a of x was, and you're like, oh, well, what's r? What's little r? Oh, well, I defined those right here. So everything is defined, including g of x and h of x. They actually define those for us. But if I wanted to expand everything out, I guess I could call this integral from 0 to 2 of, and I guess this would be pi times this stuff squared minus this stuff squared. And I'm not going to bother writing what g of x is and h of x because they define that for me. So this is just another way to write it.